Hi everyone, welcome. So I'm going to talk today about devising arbitrary convex regularizers and asymptotic normality. So this is Pierre Bellec from Rutgers, and this is for Mathematical Methods of Modern Statistics 2 in June 2020 that went virtual. So thanks for the organizer for inviting me to this virtual version of the conference. And I hope we can all meet in real life soon. Okay, so I'll present mostly two papers, mostly the first one, which is, and both of them are joint work with my colleague from Rutgers, devising. Okay, so I'm going to talk about high-dimensional statistics, almost exclusively the linear model, as we'll see in the next few slides. So we have n data points, we have p covariates, and so we are interested in uncertainty quantification, as I will define soon, in the regime where the number of covariates are larger than the number of observations. So this is the high-dimensional regime that has received a lot of attention in recent years. So today we'll be interested in confidence intervals and uncertainty quantification in this regime. So the major outcome of the literature, maybe of the last 20 years, to tackle the challenges of this high dimension in the data, and maybe the most successful methods to tackle these challenges are so-called M estimators and regularization. And so, so to tackle these challenges, a lot of solutions came to be as minimizers of optimization problems, where we minimize the data fitting term here, plus some regularizer that would enforce some structures such as sparsity, low rankness, etc., that would help us to tackle the high dimensions. Okay? And so typically in the linear model, and for regression we use the least squares loss, and these M estimators turn out to be of this form. Okay, and so we have many examples from the literature in the last 20 years. We have lasso, elastic net, bridge penalties. Here, group lasso penalties, nuclear norm penalty. If you're interested in FDR control, you may be interested in sorted L1 penalty, slope, etc., etc. There are hundreds of different examples, and now we have some intuition on the connection between the structure of the high-dimensional data and how to pick a regularizer, an additive regularizer here. So in this talk, I'll be interested in estimators of this form that I may call M estimators, but I have in mind a specific form where we use the least squares loss for the data fitting term. Okay. So when we study these M estimators, there can be different goals. Okay, so maybe initially the goal when we were studying these M estimators were to design penalty functions, so regularizer, and using intuition about the complexity of the structure in the high-dimensional data. Okay, so we can design convex regularizer, for instance, as convex relaxation of unknown structure, sparsity, low rank, etc. And we can also think about convex geometry. So, for instance, L1 balls are very spiky in high dimensions, and so this would promote sparsity. So then we can be interested in studying the performance of these M estimators. So then there are a very extensive literature now, and we understand well the risk of these estimators. Okay? And when we do so, we would like typically two things: lower bound on the risk and upper bound on the risk here. And so usually the constant don't match. Okay? And the more challenging a more challenging problem to study these M estimators is to characterize the risk exactly. Okay, so instead of having constants little c and capital C here that don't match, you want to characterize the risk exactly up to including the multiplicative constant. Okay, and so to do this, you need more precise tools. And finally, we may want to do uncertainty quantification for these penalized estimators. Okay, so uncertainty quantification meaning confidence intervals, or maybe FDR control, or some other kind of uncertainty quantification, confidence sets, etc. And so typically for confidence intervals following classical statistics, we would need some asymptotic distribution results, such as asymptotic normality or things like this. And so the point is that although there have been a lot of research on these M estimators in the last 20 years, researchers started to do 1 and then 2 and then 3, and maybe now we can do something about 4. And as you go down these goals here, more and more precise results and more precise understanding of the probability behavior of the estimators are needed, okay? Because you need more and more precise results for these type of results. Especially here for confidence interval, typically the correct scaling for asymptotic distribution, as in the central limit theorem, is to multiply by square root of n. So we're zooming at a scale of square root of n, and to understand the distributions at this scale, we need more precise results in terms of probability results. Okay. The focus of today will be confidence interval, interlinear model based on these convex regularized M estimators. Okay, so say you are interested in confidence intervals for every feature, every covariate of your design matrix. So this is what the picture we can have in mind. Okay, for every covariate, we want some way of confidence interval for the true regression coefficient beta j. So this will be the probabilistic assumption throughout most of the talk. So I'll have some design matrix which has IID Gaussian rows. The covariance matrix will be known for most of the talk. Gaussian noise, so this is very the typical linear model setting with Gaussian noise and Gaussian design. And the goal is inference in terms of confidence interval for some linear form in a direction of interest A0 here of the true regression vector. Okay, so then, and the two most prominent examples that come to mind is if you take A0 to be EJ, then you are interested in inference and confidence interval about the jth coefficient of beta. And you can also, if you want to do prediction about a new patient with characteristics x nu here, so x nu is a feature vector of a new subject, new patient, then if you're interested in the mean prediction for this new patient for which you haven't observed y yet, you can use A0 to be x nu, and this will give you confidence interval for the mean response for this new patient. So maybe the results that I'm going to present are inspired by a line of research called devising that were initially brought up to construct confidence intervals for the lasso. So there are these 3 papers that are that were very inspiring for the current work. And so when we say devising, the outcome from this literature and these 3 papers and all the papers that came afterwards is that if you have beta hat, which is an M regularized convex M estimators, A naught transpose beta hat for a fixed direction A naught will not be asymptotically normal. If you want to achieve asymptotic normality, you have to apply some correction, which I may call devising correction. And then you may hope to achieve asymptotic normality. Because the penalty function G produce some bias in the estimator beta hat. And so before going to confidence interval, you need to apply a devising correction for it to work at all. So there are a lot of results in the literature on this devising methodology for the lasso. So for instance, this 3 papers from 8 years ago, and more recent papers that are, and so all these papers are specialized for the lasso. And for the lasso, we understand fairly well how to apply the devising correction and how to achieve asymptotic normality. Beyond the lasso, the situation is more difficult. There are some results for robust M estimators without penalty. This is the line of work by El Karoui et al. There are also a large body of literature on achieving confidence interval using tools from statistical physics. And so this is the work on approximate message passing by Montanari and co-authors. So for instance, in this recent paper, it made possible to understand the devising correction and asymptotic normality results for penalty functions that have some symmetry properties. And this is because the tools from statistical physics tools require some symmetry in the data in order to be able to build this theory. There are also similar results in logistic regression without penalty. But these results are very limited outside of the lasso. And what I want to try to highlight today is that it's possible to have a general theory of confidence interval and devising corrections for any convex regularized M estimators of this form here. And so, for instance, if you are doing quantum physics, the regularizer you may be interested in here would correspond to projection on positive semi-definite matrices that have trace 1. And so for instance, in this example, there is no example of uncertainty quantification results. Okay? And so the goal of this research that I'm going to present is to avoid to constrain the practitioner in any way on the choice of the regularizer. And so I would like you to be able to use any regularizer here that you may want because of your, say, expertise, or because you absolutely want to use this regularizer here. I don't want to put any constraints on the choice of the regularizer here, and still equip the M estimator with confidence intervals. So quantity that will be very important in the results that I'm going to present is the degrees of freedom of an estimator. So what happens for these M estimators here with convex penalty G here is that if we fix X and we look at beta hat as a function of Y only, then this map here is one Lipschitz. And as a consequence, the Jacobian exists everywhere, almost everywhere by Rademacher's theorem, and so we can look at the gradient of this map. And from the gradient of this map here, we can take the trace, and this is what I call the degrees of freedom. And so this was already defined in a paper by Stein in the 80s when he introduced Stein's unbiased risk estimate. Okay, So depending on your favorite notation for gradient, you can use either of these definition for the degrees of freedom. So this is the first key quantity that I'll make use of to explain the confidence intervals for these estimators in the next few slides. The second quantity of interest will be the Jacobian itself that I denote by h hat. Okay, so the h hat is just the Jacobian of this map here. Okay, so it's a matrix in R n times n, and so if you want to take pick the degrees of freedom from the Jacobian, just take the trace. And because of some very special structure of these M estimators, for some reason H is always symmetric, and this is due to second order differentiation of convex function that we explain here. Okay, so we are equipped with these two quantities, the degrees of freedom and the Jacobian matrix H. And so now we are ready to go to confidence intervals for based on this M estimator beta hat. So the first result I'll present is for isotropic design. So I'll start with the covariance matrix of the design to be identity. This is just for simplicity because it makes it more compact to present the theorem in a slide. And this is the overall assumptions that I mentioned. Most of them I mentioned already. So we look at a sequence of linear regression problems. P and N go to infinity together, and the ratio of P over N converges to a constant gamma. So the penalty is convex. I ask for very mild assumptions such that the penalty is coercive. So it means that as you go to infinity, then the penalty must go to infinity as well. Okay, so but any norm, for instance, would satisfy this assumption. And so here, if gamma is at least 1, I also require a strong convexity of the penalty. This is for technical result. It can be relaxed in some cases, but for the general case, strong convexity helps mathematically a lot. The rows of the design matrix are IID normal. So here in the isotropy case, only for these two slides, the covariance matrix is identity, and the noise is normal as well. Okay, so this is the set of assumptions. And so this is the theorem in this setting of isotropic Gaussian design. So we look at any M estimator of this form beta hat here. So you can plug anything you want in the penalty. Say nuclear norm regularization, slope, the group lasso norms, etc., etc. The parameter of interest is we pick for a given j, a given feature j. The parameter of interest is beta j. It's just the scalar product of ej and beta. So here with the notation of the introduction, the direction of interest a naught is just the canonical basis vector is ej. As in the previous slide, h is the Jacobian, and the degrees of freedom is just the trace of h. And I also need to define some variance estimate. And so the variance estimate for the estimation of the unknown regression coefficient beta j is given here. There's the square norm of the residual plus this trace, or equivalently the Frobenius norm of h minus identity times the initial error of your estimator. Okay, beta j hat here is the jth coefficient of your M estimator here. Okay, so here is the conclusion of the theorem. Under these assumptions and with this notation, there exists a subset J of 1p of all the features of size at least p minus log p. So the asymptotic normality result here is going to hold for most indices except possibly log p. And actually, you can make this log p grow as slow as you want, as soon as the number of indices that you move aside here grow to infinity. Okay, so it could be log p or any slow, very slow function of p. And then uniformly over this set jp, this asymptotic normality result here holds. Okay, so phi t here is the CDF of the standard normal distribution. So this means that this ratio here, normalized by the square root of the variance v hat beta j, is very close to the standard normal distribution. And so here, so there is this multiplicative factor n minus degrees of freedom here, which multiplies the initial error of your estimator. So here, this is the initial error of the estimator. And then there is this term here where the residuals are projected on EJ, on the jth column of X. And so this can be interpreted as the necessary devising correction to achieve asymptotic normality and to fight the bias introduced by the penalty here. And so the first surprise when we started working on this was the scope of the penalty functions that are covered by this theorem. Okay, so basically any penalty function can be used here up to very mild conditions, such that being coercive. Okay, so for instance, any norm is going to work here if p by n is less than 1. And from this asymptotic distribution result here, so you know that this quantity is pivotal, so it is very close in distribution to the standard normal distribution, and so it's possible to construct confidence interval for beta j here, because beta j here is the only it's the only quantity which is unknown. Everything else is observed from the data. The degrees of freedom is observed from the data. You just have to compute the derivatives of your estimator at the current data. So this is observed. Beta j hat is observed. The residuals here are observed, etc. So only beta j, which appears in the variance and in the numerator here, is unknown. And by inverting, this asymptotic distribution, asymptotic normality, it's possible to construct confidence interval for beta j. And so under these assumptions, here is the result for correlated design. So now sigma is not identity, or is not proportional to identity. So you can pick any penalty function here that you want here. It just needs to be coercive and strongly convex if gamma is at least 1. Gamma is the limit of p over n here. So you pick the penalty g here, and you also pick a naught, a direction of interest here. So after the direction of interest is picked, theta, I denote with theta the parameter of interest, the unknown parameter that we wish to build confidence intervals for. So as usual, we have H, the Jacobian matrix of size n times n, the degrees of freedom here, and I define this new variance estimate v hat of theta, which is first the square norm of the residuals plus the Frobenius norm of H minus identity times the square of the initial error in the direction A naught here. I assume for the direction of interest, I assume the normalization that A naught transpose sigma minus 1. This should be sigma minus 1. There is a typo here. So I assume that A naught transpose sigma minus 1, A naught is equal to 1. And I set Z naught to be sigma minus 1, A naught. So under this normalization, this random vector Z naught is a standard normal. Okay, so this is for the necessary notation. And then based on these assumptions and notation, asymptotic normality is going to hold for most directions that you can think of in the following sense. So there exists a subset of the sphere S bar here with relative volume 1 minus something very small. something exponentially small. So this means that S bar here is a subset of the sphere that covers most of the sphere, except for some very small, exponentially small relative volume. And so for this subset, this overwhelming subset of the sphere, we have the following uniform asymptotic normality result. So for every direction in the set, in the ellipsoid sigma 1/2 times the S bar, so you can think of this as by multiplying by sigma 1/2, you are creating an ellipsoid, and by multiplying by S bar, this covers most of the ellipsoid that corresponds to sigma 1/2. Okay, and then we have that this quantity is pivotal. It is very close to standard normal. And again, we have multiplication by n minus the degrees of freedom here. Again, this is the initial error of your estimator beta hat here. Okay, this is beta hat in the direction a naught minus the true regression vector beta in the direction a naught. So this is the initial error, the initial bias of your estimator. And this term can be interpreted as the devising correction that you need to do before getting to asymptotic normality. And dividing by the variance estimate, we obtain that this is asymptotically normal. And so if you are interested in direction a naught here that are proportional to canonical basis vectors, because this is what would give you confidence intervals for the beta j's, the coefficients in the canonical basis of the regression vector. This supremum here includes at least p minus a constant in terms of the condition number of sigma times log p of the indices j in p. Okay, so this would include p minus log p canonical basis directions ej. And because typically one is interested in confidence intervals for the coefficients beta j of the true regression vector. Okay, so this is the main asymptotic normality result for in general direction a naught. And again, this quantity is pivotal and it can be used to construct confidence intervals. The confidence intervals is of this form. You just need to invert the relationship. So for instance, 95% confidence interval can be written this way. So it's all the theta in all the scalar theta such that this quantity is less than 1.96. This is the pivotal quantity in absolute value. So this is the usual way of inverting confidence intervals. It can be also done by solving quadratic equations. You just need to solve one quadratic equation, and solving this quadratic equation would give you the two boundary points of the interval. So in this form, it's not actually clear that this would produce an interval, but actually it becomes an interval. It can be rewritten as an interval after solving a quadratic equation. So if we come back to the variance term, the variance v theta here has two terms. The first term is the squared residuals, and the second term involves the initial error of your estimator. What happens is for most directions, the second term is negligible. Okay, and so using this approximation, it means that the denominator here becomes just the norm of the residuals. And then the length of the interval is very easily interpretable. It's just 2 times 1.96, the norm of the residuals divided by n minus the degrees of freedom. And then this is a confidence interval that has a form more similar to what we teach in classical statistics. So I'm going to present simulations using the approximation. So I'll use the simplifying approximation that the variance is the variance estimate is given by the squared norm of the residuals. So I construct a situation with n equal 750, p equal 500, sigma is correlated. I think sigma is taken as the realization of a V-short matrix. So the eigenvalues of sigma are still somewhat well behaved, but it's not identity covariance matrix. The true regression vector beta is the vectorization of a row sparse matrix of size 25, 10, 20. And A naught is a direction that I pick so that the estimators have large bias. And I'm going to consider 7 of these estimators, 2 group lasso estimators. So the penalty G here is the group lasso penalty with 2 different training parameters, mu1, mu2. I'm also going to consider 4 lasso estimators with tuning parameters lambda 1, lambda 4, and 1 nuclear norm penalty. So this will be the last estimator, where G is proportional to the nuclear norm. And so here in this first plot, I draw the initial errors of these estimators here. Okay, so there are 7 of them. The first 2 here are group lasso estimates with 2 different penalty levels. The 4 estimators here are lasso estimates with different penalty levels, and this one is the nuclear norm. Okay, and so we see that the initial error here in the direction A naught incurs a very large bias. Okay, here all these estimates are very far from 0. So all these 7 estimates, group lasso, lasso, nuclear norm, penalty, M estimators incur a very large bias in this direction A naught. Okay, and I picked this direction A naught on purpose. I'm looking for a direction that has a large bias, so that this bias and devising phenomena can be highlighted very clearly. Okay, so these are the box plot of these initial errors, and now I'm going to apply a devising correction. So here is the devising correction. This is the same initial error as before. This is the devising correction. So I scale by square root of n. And so it works out extremely well for all 7 estimators in the same way. Okay, all the estimates are brought back to some estimate which is centered, which is mean 0. Okay. We have the 2 pictures side by side. So these are the initial estimate without the devising correction for the 7 estimators, and these are the same estimates after the devising correction. But the devising correction exactly corrects the bias of these estimators to bring back the quantity to something that is mean 0, at least visually in these box plots. Okay. Now we want to assess for the 7 estimators. I'm going to try to assess asymptotic normality. Let's go there. So these are the QQ plots of the quantity which is close to standard normal in the theorem for the full lasso estimates. Okay, and so we see that the QQ plots are fairly satisfying. So this is the pivotal quantity for the lasso when I use the variance approximation, that the variance estimate is only the squared norm of the residuals. Okay, I drop the second term in order to have simpler confidence intervals that are simpler to construct. Okay, and so in the last QQ plot, we see that there is a visible discrepancy there is some distance from the normal distribution. Okay, the last QQ plot is not completely satisfying. But if we use instead the full formula for the variance estimate, this would fix this last estimate here. We can look at the group lasso again for the pivotal quantity, and again, so again the QQ plots are fairly satisfying. So for the group lasso and the lasso, we have an explicit formula for the degrees of freedom. Okay, so you can just plug this explicit formula for the degrees of freedom in the expression of the pivotal quantity, and that's it. It gives you the confidence interval. We now go to the last estimator, which is based on a nuclear norm penalty. And again, the quantile plot is fairly satisfying. Here, the situation is slightly different in the sense that there is no explicit formula for the degrees of freedom. Okay. But alternatively, if you are interested in a specific regularizer, if you really want to use some penalty functions such as slope or projection on PSD matrices, etc., there might not be explicit formula for the degrees of freedom. However, it is possible to compute numerical approximations in any cases for these penalized estimators. Okay, so this is what makes it possible here to construct the QQ plots and the confidence intervals when the penalty function is the nuclear norm penalty. Okay, although there is no available formula, explicit formula for the degrees of freedom in closed form, it's possible to compute numerical approximations, and these numerical approximations lead to quantile plots that are here very satisfying. So this methodology can really be used for any penalty functions, but you may have to compute numerical approximations for the degrees of freedom. Okay, so here's a short summary of the main result. So we have displayed an asymptotic normality result and given valid 1 minus alpha confidence intervals by devising any convex regularized estimator, okay, with very mild assumptions on the penalty. Okay, here you have the initial errors of the estimator after the devising correction, and these are the QQ plots that are observed in simulations. And so this is valid in the proportional asymptotic regime where P over N converges to gamma under Gaussian design with non-covariance metrics and with mild assumptions on the penalty. So time permitting, if there is still some time, I wanted to mention briefly three comments. One is on the necessity of these degrees of freedom adjustment. One is on the central limit theorems and what is called second-order Poincare inequalities that let us derive these asymptotic normality results. And the last point is unknown sigma, because in practice it's likely that sigma is unknown, you don't know sigma, and so what can be done in this case? So in the previous devising correction, there is this so-called degrees of freedom adjustment in the form of multiplication by quantity of this form, okay, depending on the normalization. So it's possible to think of this as generalization in high dimensions of the classical normalization where we multiply by the inverse or where we multiply by n minus p to obtain unbiased estimates. Right? In classical regression where p is fixed and goes to infinity. And I should mention that this degrees of freedom adjustment here was initially motivated by statistical physics arguments. So I want to talk about the necessity of this degrees of freedom adjustment because it doesn't show up in the initial proposals to devise the lasso. In these three papers, for instance, the devising the degrees of freedom adjustment is missing. So what we're interested in this paper was specifically for the lasso to understand in which regime and whether the degrees of freedom adjustment is required at all. And so it happens that if you don't use the degrees of freedom adjustment, then in some regimes, your coverage will be completely wrong. Your confidence interval will be completely wrong, okay, such that this picture. In this picture, these are supposed to be all pivotal quantity close to standard normal distribution, and without the degrees and the yellow here is without the degrees of freedom adjustment. And so we see that without the degrees of freedom adjustment in certain regimes, such that here the pivotal quantity is actually very far from standard normal. Okay, and this can be proved if the sparsity level of the true beta is greater than n2/3. So it's really necessary to include the degrees of freedom adjustment in devising methodologies. Okay, although it didn't appear in the initial proposals. So what we use to achieve these asymptotically normality results is so-called central limit theorems or second-order Poincare inequalities. What show up is random variables of this form, where Z0 is standard normal. You have Z0 transpose F minus the divergence of F, where F is some vector field. So by Stein's formula, this random variable is mean zero. And so we explained that this quantity is actually close to normal when the Frobenius norm of the gradient is negligible compared to the square norm of F itself. Okay, so this is what leads to the asymptotic normality results that I displayed earlier, and it's very flexible in the sense that if you want to show asymptotic normality, you can just mechanically compute the gradients and bound the gradients and show that this quantity is small. Yes, so you can just compute these gradients and see if you can prove the bounds, and maybe it works. If it works, you get asymptotic normality, as we showed in these bounds. And so this type of result where you can just study the gradients of a function of a Gaussian random variable, and then bound the gradients to obtain bounds on the distance to the standard normal distribution is called second order Poincare inequality. This was introduced in paper by Shourav Chatterjee in 2009. Okay, now I'll quickly conclude on what happens when sigma is unknown, because you cannot compute the devising correction when sigma is unknown. So you have to estimate. In practice, you have to estimate the score vector Z0 because sigma -1 is unknown. Okay, so it needs to be estimated. So there are several ways to do that. One way to do it is sample splitting. Although from what can be shown in simulations is that when you do sample splitting, even if you combine the estimates by switching the roles of the samples and taking some averages, that some variance is lost, in the sense that the asymptotic variance will not be as good if you do sample splitting. You are losing something by doing sample splitting. Then to avoid sample splitting, so far it should be done on a case-by-case basis for a given regularizer G. So for instance, for the lasso, one solution is called the node-wise lasso, and there are other proposals to estimate the score vector Z0. And when you do node-wise lasso, you need to do it differently, whether the direction of interest A0 is sparse or dense. Okay, there are papers by Kai and Guillaume who studied this, and we propose something in this recent paper. But because it needs to be done on a case-by-case basis, it leaves open a lot of challenging and open problems if you want to use different regularizers. So for instance, if you want to use slope, how would you do? How would you estimate the score vector in a way that is compatible with the chosen regularizer? Or if you use a penalty function, which is the nuclear norm penalty, how can you estimate the score vector z0 in a way that's compatible with your choice of penalty function? And I think there are still a lot of open and interesting problems there that I'm happy to discuss. Okay, so thank you for the time. This is the summary slide. So we've discussed asymptotic normality result and devising corrections that let you use any convex penalty functions and construct valid 1 minus alpha confidence intervals. This is valid in the asymptotic regime where P over N converges to a constant with Gaussian design. I hope you're all safe and you enjoy the talk, and I'll finish here.